Okay, so this is our lecture number 3 on solving this fast paper example. Okay, so this is the example 9.9.43, right? And in this example 9.43, we are asked that the figure 9.37, which is this is figure 9.37, right? And okay, so this is figure 9.37, and it's asked that the portion of titanium copper alloy. So titanium and copper alloy phase diagram is shown, right? It says to specify all the temperature composition point at which the eutectic, eutectoid, pre-eutectic, and congruent phase transformation take place, right? Okay, so first of all, it is very necessary for you to know what is eutectic, what is eutectoid, what is pre-eutectic, and what is congruent single phase transform, right? Okay, this is liquid, this is beta, and this is, I think, beta plus liquid, right? And this is again this is what we call the Ti2Cu, right? And this Ti2Cu, and this is alpha phase, right? And this is intermediate beta plus alpha, right? And this is TiCu, TiCu4, right? Okay, so let's come to first our first reaction, which is eutectic. Okay, so I told you already in the chapter the eutectic is the point with which the one liquid converts to two solids, right? Or the liquid completely transformed to directly transformed to a solid, right? So in our case, we see that here is liquid and here is again the mixture of two solids, which are Ti2Cu and TiCu, right? So this is a mixture of these both solids, right? So this occurs at about uh, 50 58% Cu. It occurs at this point, and the temperature is almost, if we draw a horizontal line, right? If we draw a horizontal line straight, right? So it is almost above 950. This is 1000. This is 1000, and so it almost occurs at 965. So temperature is 965, right? But the eutectic on the eutectic reaction is that liquid is converting to these two solids, Ti2Cu and TiCu, right? So our eutectic reaction is this, right? And in the second part, we have to find the eutectoids, right? So I already told you that the eutectoid is a reaction in which the one solid convert to two other solids, right? So if you look at the diagram, then you will see that this is the beta phase, right? And this beta phase is converting to these two solids, right? And these two solids are alpha plus Ti2Cu, right? This is the uh, formulation for this, right? So one solid is converting directly to two solids. So our second reaction is eutectoids, right? So it occurs about this is 10, so it occurs about 8, right? 8 weight percent of copper, right? And the reaction is this beta converts to alpha plus Ti2C4, and the temperature corresponding to this point is almost, if we look, this is 800, so this is just below the 800. So we will draw the temperature is 795 degrees centigrade, right? Okay, so now for our part C, we have to determine the pre-tactic. Okay, so it is very necessary for you people to understand that what is pre-tactic, right? So the pre-tactic is basically a reaction in which a solid and a liquid, solid plus liquid, they convert to another solid, right? So if we look at our diagram, so this is the solid plus liquid part, right? And when we look at this diagram, then we are mm, automatically uh, we automatically assume or we automatically come to a conclusion that it it almost it at this point, right? This is the point, right? And at this point, it converts to another solid, right? And which is almost at about okay. So this is which is just above the 1000 temperature. So our temperature for the pre-tactic, the temperature is like almost 1000 and just above. So I will write 1000, right, 6 degrees centigrade, right? And what is the reaction? So the reaction is that beta plus liquid, they both are converting to another solid, which is here is TiCu, Ti2Cu. So it is dititanium copper, right? So this is the pre-tactic reaction, and the composition of copper here is 40%, right? 40% Cu. Okay. So now for the part C. Okay. So in the last part of this question, we have write the congruent phase transformation, right? The congruent phase transformation. Okay. So it means that the liquid a liquid is converting directly to a solid, right? Liquid directly convert to solid, one solid, and basically this is the melting point of this solid, right? So we have to look at this melting point because it says the congruent phase transformation, so it occurs congruently, right? So if we look at the diagram, this is the liquid diagram and it converts to beta plus liquid, so it is not a point of concern. Here it converts to a solid, it is not a point of concern, right? But we should look something like here, right? Okay. So if we look at this point, then we see that this liquid is directly converting to TiCu, right? So this is basically the melting point for the this titanium copper. Uh, so this titanium copper, this convert to liquid, or liquid converts to titanium copper at this point, and this is basically our congruent phase transformation reaction, right? So our congruent phase transformation reaction for this is this, right? So the liquid convert directly to TiCu4, and if we draw a horizontal line, right, and if we connect it in, it just falls below this. So the temperature is above 950 but below the 1000, so the temperature is almost 970 degrees centigrade, right? Okay, so if the temperature is 900 and it occurs about if we draw a straight vertical line, right? So it is in between 60 and 50, and it just below 60. So the weight percent composition of copper is almost 57%, right? Okay, so this is all about this question, right? Okay, so our next topic is about these TTT diagram, right? So time dependent transformation, right? Okay, so uh, in these diagrams, basically we look at the equation that are governing the isothermal transformation, right? So for example, if you look at this in this T2 temperature, right? And if you go along this temperature with respect to this log of time, right? So this is actually log of time scale, and this is the temperature scale. So if you move, then you will see that here is the perlite, right? So this is basically a phase diagram, a TTT diagram for the iron carbon alloy, right? Okay. So the perlite at the start, and then austenite plus perlite here, right? And when you move down here, then it will have the coarse perlite. So perlite and the what we call the benite and benentite and austenite and the metastable austenite, right? So and the martensite, they are basically the forms of steel, right? So steel have different forms at different temperature, and we are basically want to know its microstructural changes along a constant temperature. Okay, so for example, you heat up this is the crucible, right? And you heat up this by applying the flame, right? And after some time, you notice here, right? So let's say the temperature is 250 degrees centigrade. Okay, so if you let the temperature remain constant and you and the time is increasing, right? So you will notice, let's say the temperature is T2, right? So you will notice that the perlite, after some time, it transforms to austenite, and then after some time it transforms to perlite, and then to the coarse perlite, right? So basically these graphs, they are basically isothermal phase transformation diagrams, right? So isothermal means that at constant temperature the phase of these different alloys, they changes, right? So now this is our question. It says that how fine perlite is produced in the time temperature transformation, right? So from the previous diagram, you see that here perlite is forming, right? So the time temperature diagram was looking like this, right? Okay, so here was perlite. So when you go along this line, right? So above at very high temperature, here will be coarse perlite, and below which there will be fine perlite, right? So you will just mark this perlite diagram, right? And you will see that the perlite here is fine, right? Okay, so this is another I just included it here because it is the time transformation diagrams, right? Okay, so when you see that here is austenite, fully austenite at this point C, right? But when you move intermediate between these two, right? Then you will see that here is the microstructural changing are producing take place. But if you let the time to increase more, then you will see that the ferrite and the iron carbide they formed, right? So this here above there is coarse perlite, and when you move down, right, so here is fine perlite. So you have to notice there that just below, just close to this line, here is coarse perlite, and above there is fine perlite. Okay, so now this is another question from your. Okay, so this is a question, right? And it says that in the following phase diagrams, right, mark all the phases, right? Uh, Draw the microstructure of A and B, right? And write down the invariance reaction at C. Okay, so already you will notice that here is liquid, and here is liquid plus another solid. Here is another solid called gamma, and here is gamma plus alpha, and here is alpha plus beta, and this is alpha. Okay, and there is also alpha. This is liquid alpha, right? And here is alpha plus beta. This is alpha plus beta, and this is beta, another type of solid. Okay, so we have marked out the pages, right? And now it says that draw the micro structures of A and B. Okay, so at A, here is only gamma, right? So it will look like something like this, and like this, like this, and this, right? So this is gamma, right? Okay, and now what about point B? This is our point B. Our point B is composed of two solids, right? One is alpha and other is beta, right? So you will notice that first of all it was gamma and then transformed to alpha plus beta. So let me at this was at point A and at point B, right? So let me draw with the help of other colors, right? Okay. So these on the red, they are alpha, right? Okay. And here are some particle of beta, right? Okay. So this is uh, this is alpha and this is beta, right? Okay. Now, mm, also it stated write down the reaction at C, right? So at C, if we look at the diagram very carefully, right, then we can draw this reaction at C, right? But at C, we got that alpha plus beta, sorry, the gamma plus beta, they are both converting to alpha plus beta, right? Okay, so let me zoom out this point C and tell you that whether the reaction that is happening there is a constant entity or not, right? Okay, so at C, if you look carefully at C, right, then uh, there are two possibilities, right? Hmm, what is this possibility? Okay, okay, so above point C, here is gamma plus alpha, right? Okay, let me draw. This is point C, right? Here is gamma plus alpha, and here is gamma plus beta. Sorry, this is gamma plus beta, and here is beta, right? Okay, this is power beta, and this is alpha plus beta, right? Okay, so if we from point C, right, from point C beyond upward, uh, this is basically going to the composition percent of beta, right? Okay, so at constant temperature, if I draw a line, right, then it will look like something like this, right? And I notice that this gamma, uh, it is converting directly to alpha plus beta, right? So this gamma is converting directly to alpha plus beta. This is the reaction at point C, right? Okay, now this is an interesting question from your past paper, right? And it says that draw the phase diagram between A and B, right? For the unlimited liquid and solid solubilities where A and B have melting points of 850 degrees centigrade and 600 degrees centigrade, right? Also draw a binary eutectic system diagram between L and 10 when they exhibit unlimited uh, mutual liquid solubilities, right? The melting point of lead and tin are 232 and 327. The eutectic composition and temperature are 384, sorry, 38% Pb and 183 alpha. Okay, so for part A, here we are given A and B two solids, right? Okay, and A have the melting point Tm for A is 850, and for B it is 600 degrees centigrade. Okay, so so if we look like a typical diagram, right? A typical diagram, it will look like this, that here will be the solid region for the binary eutectic system, and here will be the liquid plus, let's say alpha is our solid and here is liquid, right? And here is our alpha, right? But they should converge at the same point, right? Okay, let me draw again. Okay, so this is my temperature line, right? I will draw first of all a box, and this is the, let me draw the composition of A here, right? So it is 0% here and 100% here, uh, right? Okay, so it means that here is pair B, right? Here is pair B and here is pair A, and here is pair B, right? Okay, so for A, 850, so I will mark a temperature of 850 degrees centigrade, right? And for B it is 600, so 600 will just lie below the B, right? So it will be 600, and then I will draw a diagram which will meet these 2 points, right? Okay, so this is alpha and this is liquid plus alpha and this is alpha solid, which is a binary eutectic system for both the temperatures, right? Okay, so this was the answer to our part A. What about part B? Okay, for the part B, you will draw a general eutectic reaction diagram, right? You have to remember this diagram if it is asked in your exam, right? And you will draw the temperature axis, right, and the composition axis. Okay, so when you draw these composition axes, right? Okay, so here we notice that here was our alpha region, right? And there was a point, right? And this was the beta region, right? And here was, they both were connecting by a line, right? And one was from here up to here, right? And from there up to, which connect to the beta region, right? So this is beta plus liquid, this is alpha plus liquid, and this is liquid, this is alpha plus beta, right? Okay, so now it says that the melting point of lead and tin are 232 and 327, right? So let's say I draw the Pb here, Pb weight percent, right? Pb is lead, right? and 10 is Sn is 10, and Pb lead. And this is 0% and this is 100%. So it means that this is paver lead and this is paver tin, right? So per paver tin, we have a temperature. Use the melting point of lead are 232 lead. Okay, so lead is here is 232, and for the tin it is 327. So you will mark 327 here. And the eutectic reaction, they occur by 38%. So this line correspond to over 38% Pb, and the temperature you should dry is 183. Okay, so this is the answer to our part B. Basically, the point in memorizing these diagrams is that you should know that at least it is coming in your exam, right? Okay, so it says that this is the example from your past paper. It said that determine the Miller indices for the planes shown in the unit cell, right? So it is our plane A and it is our plane B. Okay, so there are three steps when you determine the Miller indices of each uh, plane, right? So for each plane, you will first of all locate its origin, right? So almost its origin is here. This is the origin, right? Because the x sorry, this is the x-axis, this is the y and z, right? So x-axis is positive when you move along this point, it's negative when you go backward. When you go to the right side, then y is positive. When you go to the left, then y is negative. And when you move up, this is positive z. You move down, this is negative z, right? So you have to remember these coordinates when you draw the Miller indices of any of the plane, right? Okay, so I will draw first of all for plane A. Okay, so I will first of all look at the x, y, and z intercepts, right? So the x-intercept, we look at, this is the x-axis, and this is the positive x-axis, right? So the x-intercept is 1 over 3, right? And the y-intercept is again positive 1 over 2. And what about the z-intercept? If you look at the z-intercept, it is in the negative direction, right? If we choose our origin as this, right, then you look at this is positive, this is positive, but this is negative because it is moving downward, so it is negative 1 over 2. Okay, so now the second step for the Miller index is that you take the reciprocal of these, so it is 3 2 minus 2, right? So 3 2 minus 2 is the Miller indices. Sorry, you should write hyphen above this. So the Miller index, if I write in a correct form, then it is uh, 3 2 and a negative 2, right, like this. So for the plane A, the Miller index is this, right? And for the plane B, if you look at the plane B, right, so where it touches the x-axis, right? So plane B. Okay, so this is our point of contact. This is point of contact, this and this one, right? Okay, so x, y, and z, right? Okay, so where it is cutting the x-axis, right? If you look, this is our x-axis, right? Okay, so our x-axis is cutting at x is equal to, let I take this is the origin for the plane B, right? So at x-axis it is 1 over 2, right? For the y-axis, you notice that this is the y-axis, right? And this plane is parallel to the y-axis, right? So it does not cut the y-axis, so I will write infinity because it does not cut the y-axis. And for the z-axis, if you uh, if you notice here, right, so it cut the z-axis at this point, right? It is it is given at 1 volt, right? But my origin, I almost located at this point. But the negative sign, it depends upon your origin, that where you take your origin. So I take the origin at this point, so my point will be 1 volt, right? Okay, so the third step in the Miller index is that we take the reciprocal, right? Okay, so when we take the reciprocal of this, then what should be our answer? Our answer will be 2, and 1 over infinity is 0, and 1 over 2 is 2. So our answer is 2, 0, 2. This is the Miller indices for this problem. Okay, now let's come to this interesting question, right? Okay, so it says that which crystal system does the unit cell have belong to? Okay, so if you look at the A and the B and the C, so A is 0.3. A is basically the distance along the x-axis, right? So it is 0.3. B is the distance along the y-axis. It is also 0.3. And C is along the z-axis, so it is 0.4. So we see that A is equal to B is equal to 0.3, but C is not equal to B is not equal to A, right? Okay. So this system, and also if we look the angle of x-axis, y-axis, and z-axis, they both are the same. So alpha is equal to beta is equal to gamma. They both are 90 degrees right angles, right? So for part A, our answer is tetragonal. Sorry. Okay, so we call this system as tetragonal, right? For part A, answer is tetragonal, and for the part B, right? In the part B, it says that what would this crystal structure be called? Okay, so since there is a center element, right? So this look like this, that this is a box, right? Box, and at each corner there is one atom, right? And in the middle, if I draw the middle correctly, so this is the middle and here is the middle atom, right? So it is the body-centered tetragonal cube. Sorry, it is not a cube, it is a tetragonal system, right? So it is body-centered tetragonal, right? Because there is a central atom. Okay, now in the next step, we calculate the material density if uh, the atomic weight is 141 gram per mole. Okay, so A is given to us, it is 141 gram per mole. Okay, so we will use the simple formula for the density of the material, right? So when we know the atomic mass of an element, right, then we can calculate its density. Density is basically rho represented by rho, and rho is equal to n times A divided by Vc into Avogadro number, right? Okay, so we have to find this Vc and n, right? So n can be calculated from the body centered cube. So we have 8 elements at the corner. So 1 over 8 it contributes, right? And 1 at the center, right? So it will have 1 plus 1, so it had 2 atoms per unit cell, right? So in this unit cell, 2 atoms are there. And what about the volume of the cube? Volume we can calculate by length multiply breadth multiply height, right? Length multiply width multiply by height, right? So length is 0.3, 0.4 into 0.3 into 0.3, right? And this all in nanometers, right? So it is 3.60 uh, into 10 raised to the power minus, uh, if we convert it into a centimeter every side, right? So it will 10 power minus 8, 10 power minus 8, and 10 power minus 8. So it will constitute to 10 power minus 23 centimeter cube, right? Okay, so let me explain this step to you, that how I convert from nanometer cube to centimeter cube, right? Okay, so our length is 0.4 nanometers, right? So nano means 0.4 into 10 raised to the power minus 9 meters, right? Okay, so let me now find the volume, right? So volume is 0.3 multiplied by 0.4 multiplied by 0.3, which is, if I multiply it by my calculator, it will give me 0.3. So it gave me 0.036, and there are three nines, right? So into 10 raised to the power minus 9 3 is 27, so it is minus 27, and it is in meter cube, right? Now I want to convert it into the centimeter cube, right? So what should I do? I should simply multiply this with the help of uh, conversion, right? Is 10 power minus 6, right? So when I multiply it when I convert to centimeter cube, right, then it gave us 3.60 into 10 raised to power minus 23 centimeter cube, right? So I just multiply the this term, right, with the 10 power 6. So when I multiply it, then it will give my answer to be in 3.60 into 10 raised to power minus 23. Okay, now we know VC, we know N, then we can use this equation, right? So how can we use this equation? Let's use this equation. Okay, so when I use this equation, then it is give us that rho is equal to NH2, right? So 2 into the atomic weight percent is 141, and VC we calculate just it is 3.60 into 10 raised to power minus 23, and the Avogadro number is 6.023 into 10 raised to power 23 atoms per mole, right? So when you do the calculation, it will give you 13.21 uh, gram per centimeter. So this is our answer to part C. Okay, now let me explain to you an interesting phenomena called creep, right? So what is creep? Creep is time-dependent deformation. So I already explained this concept in the lectures, but let me revise you, because it is very important from your exam point of view, because uh, there are basically um, the y-axis is the creep strain and the x-axis is time, right? So let me explain to you that what is the creep strain, right? So let's say there is a machine operating in a factory environment, right? Okay, so this is a shaft and this is the motor. This is the motor and it is connecting with the shaft, right? So there are bearings, there are gears, a lot of these, right? So they will apply a constant load on this shaft. Apparently, it is not, it is below the yield, below, it is below the yield stress, but these stresses are for a very long time, right? So for a very long time, they will deform the shaft, and this deformation is called the creep strain, right? Similarly, if the temperature of the factory is high, but it is far below than the melting temperature, Although from the material mechanics of material point of view, we notice that here will be no deformation, but the temperature is causing something deformation, and that deformation also come in the creep strain, right? So this is the whole phenomena of creep. Now when we draw the creep strain with respect to time, then it give a graph like this, right? So at first we will notice the instantaneous deformation, right? So basically there are fi. Okay, so our start will be from the instantaneous deformation. Okay, so instantaneous deformation will occur here, right? This occurs because we don't know that why this, but the creep strain will occur like this at instantly with no time. It will not require it, but it will happen very suddenly, this deformation, right? Okay, when it start, you will see that it accelerates, right? The slope of the graph is negative here. So this will be a very slow, very slow, very slow. Okay, so in the primary region, negative slope, and here it is negative slope, decreasing strain. So these are the characteristics of the primary region, right? And one more thing we observe here that the deformation is very slow. So this is the primary region, right? Now, when we move to this, the secondary region, right? So our primary, we are done with the primary region, right? So we are done with the primary. We are done with the prime. Now, what about the secondary region? So the secondary region have a constant slope, right? Uh, the rate is constant, right? And why the rate is constant? The third property is that it is the slope is balanced. The strain is balanced by strain hardening. Okay, so this is the most important point, that strain hardening is occurring there, right? So the strain hardening is occurring there, and that's why this property of the material, that this deformation is balanced by the strain hardening. So that's why it gave us a constant slope. Okay, and now we come to another most important region, which is called the tertiary region, right? So when we look at the tertiary region, we are basically we basically note that the rate of deformation, let me write again here, strain hardening is occurring, right? And when we look at the tertiary region, so let me draw the properties of it, right? Okay, so what are its properties? Its properties are the slope is increasing faster rate, crag growth. Okay, so the cracks in this region, they start growing, right? very fastly, and the faster rate of creep, and the slope is positive, right? It is increasing. Uh, and it will eventually lead to a rupture point, right? Rupture point. So this is the rupture time, TF, right? So from this 0 to TF, basically this is the point for creep. And one thing that I would like to, you to inform about the creep, that this phenomena is very, did take a lot of time. So it is not very noticeable, but it is important for you guys to understand this, since an engineering point of view, you will design these things, right? So that's all about today, right? See you next time. Thank you.